Chapter 8 Extra Topic Trigonometric Substitutions. Trig substitutions is not a topic covered on the advanced placement exam. However, you might see it in college. The photo is of Thomas Jefferson's home, Monticello, near Charlottesville, Virginia. We can use right triangles and the Pythagorean theorem to simplify some problems. We'll use this right triangle as our model. The integral of dx over radical 4 plus x squared. These are in the same form. If I make the lower side 2, then the hypotenuse becomes radical 4 plus x squared. Secant theta equals radical 4 plus x squared over 2. 2 secant theta equals radical 4 plus x squared. Tangent theta equals x over 2. 2 tangent theta equals x. 2 secant squared theta d theta equals dx. Now we can substitute in. For dx, we put 2 secant squared theta d theta, and for radical 4 plus x squared, we put 2 secant theta. We can cancel a 2, cancel a secant theta. Now we have the integral of secant theta d theta, which is the natural log of the absolute value of secant theta plus tangent theta plus c. Now we substitute back in. Secant theta is radical 4 plus x squared over 2, and tangent theta is x over 2. So we get our answer, natural log of the absolute value of radical 4 plus x squared over 2 plus x over 2 plus c. Since we have a common denominator, we can combine the terms, and then we can separate the natural log into the log of the absolute value of radical 4 plus x squared plus x minus the log of 2, and the plus c comes straight down. But ln2 is a constant, so our final answer is ln absolute value of radical 4 plus x squared plus x plus c as we combine the constants. This method is called trigonometric substitution. If the integral contains radical a squared plus x squared, we use the triangle at right. If we need radical a squared minus x squared, we move a to the hypotenuse. And we get this triangle. If we need radical x squared minus a squared, we move x to the hypotenuse. And get this triangle. Example 2, the integral of x squared dx over radical 9 minus x squared. In this problem, a is 3, so we move a to the hypotenuse. Now we select our substitutions. Sine theta equals x over 3. When we're choosing which trig functions to use, in general we try to find trig functions where the variable is in the numerator. 3 sine theta equals x. 3 cosine theta d theta equals dx. Cosine theta equals radical 9 minus x squared over 3. 3 cosine theta equals radical 9 minus x squared. Substituting, we get the integral of 9 sine squared theta times 3 cosine theta d theta over 3 cosine theta. We cancel a 3 cosine theta, and then we use the trig identity to rewrite the problem as 9 times the integral of 1 minus cosine 2 theta over 2 d theta, having factored the constant 9 to the outside. We can factor out the 1/2, and we get 9/2 integral of 1 minus cosine 2 theta d theta. Taking the antiderivative, we get 9/2 theta minus 9/2 times 1/2 sine 2 theta plus c. But sine theta was x over 3, and theta equals inverse sine x over 3. So we have 9/2 inverse sine x over 3 minus 9/2 2 sine theta cosine theta plus c, using a trig identity again, the double angle formula. Finally, substituting back in, we get 9/2 inverse sine x over 3 minus 9/2 times x over 3 times radical 9 minus x squared over 3 plus c. Simplifying, we get 9/2 inverse sine x over 3 minus x over 2 radical 9 minus x squared plus c. Example 5. Integral dx over radical 2x minus x squared. We can get 2x minus x squared into the necessary form by completing the square. Start with 2x minus x squared. Factor out a negative sign, so we have negative quantity x squared minus 2x. Then take half of 2 and square it to get 1. But since there's a negative sign in front, we're actually subtracting 1. So we add 1 here. Now we have negative x minus 1 quantity squared plus 1, or 1 minus the quantity x minus 1 squared. So our integral becomes dx over radical 1 minus x minus 1 squared. Let u equal x minus 1. du equals dx. So I have the integral of du over radical 1 minus u squared. Using this triangle, we see that cosine theta equals radical 1 minus u squared over 1 equals radical 1 minus u squared. Sine theta equals u. Cosine theta d theta equals du. So now we have the integral of cosine theta d theta over cosine theta. Cosine theta cancels out, and we just have the integral of d theta, which is theta plus c. but theta is equal to the inverse sine of u. So we have inverse sine u plus c, and u was equal to x minus 1. So our final answer is inverse sine x minus 1 plus c. And of course, you might have recognized that form without having to do this work. Example 6. The integral of dx over 4x squared plus 4x plus 2. Complete the square. 4x squared plus 4x plus 2 could be written as 4x squared plus 4x plus 1 plus 2, or 2x plus 1 squared plus 1. Now we have the integral of dx over 2x plus 1 squared plus 1. Let u equal 2x plus 1. du equals 2x. 1/2 du equals dx. Now we have 1/2 times the integral of du over u squared plus 1. Once again, you might recognize this form, but let's continue with trig substitution. We use this triangle. Tangent theta equals u. Secant squared theta d theta equals du. Secant theta equals radical u squared plus 1. So secant squared theta equals u squared plus 1. Our integral becomes 1/2 integral of secant squared theta d theta over secant squared theta. Secant squareds cancel out, and we get 1/2 integral of d theta, which is 1/2 theta plus c. But since tangent theta equals u, theta equals inverse tangent u. So we have 1/2 inverse tangent u plus c. But u was 2x plus 1. So our final answer becomes 1/2 inverse tangent 2x plus 1 plus c. Here are a couple of shortcuts that result from trigonometric substitution. The integral of du over u squared plus a squared equals 1 over a inverse tangent u over a plus c, and the integral of du over radical a squared minus u squared equals the inverse sine u over a plus c. These are on your list of formulas. They're not really new.